thanks for being here, and again for the other presenters, thanks for being flexible with the order of presentation. A little bit of background of this particular talk. Actually, this is born of something that we do internally at 51. We have this paper reading meetup group where each one of us that are interested in research finds an interesting paper that they like and kind of presents it to the team. And I really like the ideas that are going to be presented in the two papers that we are going to look into today, so much so that I've actually turned them into parts of our workshop. So the original talk here is meant to be 45 minutes, but I'm going to condense it down to a lot smaller than that. So it might feel like we're going a little bit fast through there, but if you're interested in learning more, hit me up. Maybe I'll write a blog post about it, or if you want to have the workshop come to your city, let us know. We'll be happy to do that. All right, so there's an issue when we're creating data sets that are scraped from the internet. It requires a ton of resources to label it and come up with annotations. There is an abundance of readily available web scraped data, but we can't just use this massive unfiltered data set that's scraped from the web. It doesn't guarantee good model performance, mostly because the web data and images have inaccurate captions and just noisiness in general. Like it's not all high quality, and this is really important for visual AI use cases because we want to have good labels, good annotations. Traditionally, folks have been using Clip to curate these large-scale data sets. It's a great first line of defense. It lets us efficiently and effectively measure, well, effective to a certain extent, whether what's in our image matches what's in our caption. But the thing with Clip is that it has its limitations. And so let's talk a little bit about those limitations. So what does Clip do? It gives us a broad similarity score between an image and text. But with Clip, you might get a high Clip score even when it's missing some of the key objects that are mentioned in the caption. It looks at the overall picture and kind of what's in the image, but it misses details. And this is problematic for, let's say, creating a data set for object detection, because we need to have more precision for that. We need bounding boxes. We know what's in the image and what's not in the image. And so these two papers kind of arrived at a similar conclusion that we need to rethink how we filter our data set, especially for object detection type of use cases. Both papers point out that current go-to methods like Clip, while they are powerful and a good first line of defense, they might steer us wrong, and it has limitations, but it's powerful when it's combined with other methods. So that's what these two papers are primarily dealing with. I'm going to talk to you about these papers using the PACES method. PACES was written, as a method by Jason Corso. He's our chief science officer here at 51. I'm sure Jimmy will drop a link to the blog. But essentially, we're going to look at the problem. We're going to identify the paper's main technical focus and its context within the literature, summarize it, state the main claim, discuss any evaluation that was done, and then present what the substantiation was. So for the first paper, the problem here is that large web crawled data is been trained to perform, been used to train high-performing multimodal models, but the data often contains low-quality and noisy samples. The approach that this paper is proposing is to refine the web-crawled data by using different filtering techniques, okay? And then we combine these filtering techniques and use some ensemble of them, essentially. And so here, this is the other paper. This paper takes a step further. So it says, okay, let's use Clip along with grounding Dino and start kind of being more grounding the captions in the images. So we'll talk about what this means in a second here. So let's just do a deeper dive into the first paper I presented. So the first paper is just a step-by-step method that's all about creating data sets that are tailored for object detection specifically. And the method they propose is about kind of prioritizing this notion of scene complexity and object diversity rather than just relying explicitly on clip. So what they do is they first established an initial data pool, just a huge, massive amount of data. In this case, they used the data comp data set, which is like 12.8 billion samples. And they applied a bunch of filtering criteria. So for example, first they filtered it down to only images that have English captions. And then they also applied a filter that says, okay, now we only want images that have a minimum resolution of 200 by 200 pixels. And then on top of that, the aspect ratio of the pixels, right? Once we have this minimum width and height set, that ratio, the aspect ratio should be greater than 0.3. Then they did something called detection-aware filtering. So they filter the data set kind of with this kind of what they call detection-specific criteria. We'll get into this in a second. But this is different from just clip filtering, which is just relying on image text alignment. And what they do is they use the RPN network, so they call it RPN filtering, and they have two different types of filters. One is called object class entropy filter. So it essentially, after doing the initial filtering that we had just discussed, they use a pre-trained object detector. This pre-trained object detector will generate pseudo labels for all the other images that are in the data set. The pseudo labels can be the object category, they could be confidence scores, as well as bounding boxes that localize that detected object. Then they apply a confidence threshold filter to filter out kind of the unreliable pseudo labels. And they've shown that this actually works well when you have a decent threshold. So of course, this threshold is something that you need to experiment with. This and hyperparameter that you need to learn as well. And then from there, you can now take that data set and then do some kind of further training on it and whatnot. But we're not going to get too much into the pre-training and evaluation of the detector. We're primarily worried about or focused on rather the curation methods. So this detection-aware filtering that I had mentioned in the previous slide, I just want to walk you through kind of what they propose here. So they have a pseudo labeler, which is just a pre-trained object detector that's going to look at each image in the data set. But instead of using it for like a traditional object detection type of task, they kind of use it as a smart filter. So there's two main stages. There's the RPN filtering, right? And so this RPN filtering, this is all about if you look at the pseudocode here, it kind of tells you what RPN filtering is do. Take an image with this object proposals, count how many proposals exceed that confidence threshold, but then only keep the images that meet that minimum proposed threshold. And for this, they specifically in this paper use a two-stage object detector. And so in the paper, they used faster RCNN. And they do this because it's a little bit more robust when you're dealing with different types of data set. Because we're then going to create another filter called entropy filter. And if you look at the pseudocode, what it's saying is that we're going to create a frequency count of object classes in each image, convert those to probabilities, and then calculate the entropy to measure some notion of diversity of objects in that image. So higher entropy means higher diversity, and that's what you want. And you can, of course, experiment with that threshold. In the paper, they used the 75th percentile. But in any event, both of these are sharing the same goal. They want to identify images that have rich complexity and rich in objectness, regardless of how well it matches the text description. So just to go a little bit more detail, I'll go quickly over this to be mindful of time. So every image, with a two-stage detector, every detection that you get will have the proposals with 4 pieces of information. So there's PB, OB, LB, and CB. PB is the bounding box coordinates. OB is the objectness score, which is how confident we are that there's actually an object there. LB tells us what the object likely is, and CB is how confident we are about that label. And so the filtering process is pretty straightforward. We have 2 key thresholds. In the paper, they say and when you're working on your own data set, this is something you set for yourself, but you want at least N proposals per image. In the paper, they say 10, with an objectness confidence above 5. And they suggest these numbers because, in their experimentation, they're using the LDIS data set. They found performance to plateau after about 8 to 10 boxes. Now for entropy filtering, so instead of just counting objects, you want to look at a variety of objects. So you can use the same detector to identify objects, but now you just count how many different types of objects we see. And so they use, again, entropy to do this. And they set a value to be in the top 25% in the paper, but of course, in your use case, you can experiment with this. All right. Hopefully you guys are still with me. I know I'm going through a lot. This gets a lot more detailed in the actual workshops, but let's talk about the next one now, the next paper. And this is using, again, a two-step data curation framework. It's going to combine object detection and filter ensembles this time to refine this large web scale data. So again, this paper is a little bit different. Like the previous paper, they don't really rely on CLIP at all. In this paper, they say we're still going to use CLIP, but we'll build on it a little bit with some other type of filters. And so we'll talk about those filters in a second here. So they use grounding dyno in the paper, and they use grounding dyno to identify objects that are mentioned in the caption, and then from that we can get the location, bounding box location, the confidence score, as well as the caption kind of gives us a prompt so we can find what the actual object is as well. And they state that this addresses the limitation of using CLIP alone, because now instead of getting an overall measure of image and text similarity, we're getting more concrete information, if you will. So again, we start with an initial CLIP filtering just because it's fast, efficient, and it works, and we can quickly remove image text pairs that have low semantic alignment. Then we move on to object detection with grounding dyno. We get the bounding boxes of the detected objects. Then we get the predicted logic scores, and then we see the phrases that correspond to each detected object. And then from there, we can design object detection filters. And so these object detection filters that we're going to see actually in a second, have two main purposes. We want to eliminate false positives. Well, actually, that's the main purpose. We want to eliminate false positives. That's the main reason we're going to use these filters. And it also gives us granular information so that we're able to effectively use our filters. So let's talk a bit about these filters. This is just an example of potential filters you could use. I just kind of wrote the function signature and doc strings of potentially what this could look like for you. So, when we run grounding dyno through an image, we get bounding boxes, predicted logic scores, and then the phrases for each detected object. So then each filter is going to take the input, and we're going to make a binary decision. Do we keep this image or do we reject this image? All right, so we create the grounding dyno filter. Again, this is just based on the grounding dyno outputs. We create a logic score filter, and this is meant to select images that are kind of based on the average or maximum logic score of the detected objects. And we want to eliminate images where the grounding dyno has given us low confidence in its object detection. So that way we're removing, again, image text pairs where object might be misidentified or poorly localized. And for this logic score, there's two different variations they discuss in the paper: average logic score filter and then maximum logic score filter. So average, again, it's kind of what it says on the tin there. Calculate the average logic score across all the detected objects in the image, set a threshold, and discard images that have a low score. Maximum says, okay, consider the maximum amongst all the detected objects and make sure that at least one object is detected with that confidence. There's another number of detected objects filter. So this is similar to that filter in the previous method where we're looking at like the objectness of an image, trying to capture its visual diversity, and of course an aspect ratio. So a little bit of overlap between the two methods, which to me suggests they're both kind of onto something. Okay, so we've got a bunch of filters here. How do we kind of use them together? So they have this kind of ensembling approach that they discuss in the paper. So we start with the raw data set, have the image text pairs, apply our filters, and once we have our filters, each filter is going to produce something they call an inclusion label. Says either we include it or we don't include it. What we want to do is to find a set of data points with inclusion labels that are going to comprise essentially a refined data set, right? But trying to, if you've got a number of different filters, like the combinatorics that could explode, right? You could, of course, take a majority vote, but the thing about a majority vote is we're going to treat all the filters equally. We're not accounting for differences in their accuracy, and it's not actually considering the correlation between the filters. So they say, all right, well, we can use weak supervision to kind of bypass that. And so they propose using the icing model. And it's essentially kind of like a group decision-making process where you have a lot of experts, these filters, and they each have a different level of, biases. They have a different level of expertise, if you will. So the different correlations, and the icing model is going to help you figure out how much trust each expert, like how much should you trust each expert, and how their opinions might potentially kind of influence each other, if you will. So I'm not going to get into details of this here in the longer presentation I do, but note that this is the method they use, the icing model via weak supervision. All right, great. That's good. Let's combine these ideas now and kind of come up with the end-to-end workflow for how we might approach this in our own kind of our own tasks here. All right, so let's just say you have an end-to-end, you want to essentially create a zero-shot model, let's say, or you want to come up with a curated data set to train another or fine-tune another model on. So first thing you should do, data set preparation, get your data, do some initial processing. So, either that initial processing can be some super simple thresholds, remove images that are too bright, too noisy, too dark, contrast off, things like that. And then from there, step 2 is you can employ this zero-shot object detection model. So you can choose a pre-trained model, like Grounding Dino if you want, YOLO World, whatever, up to you. And we're trying to do some kind of essentially pre-labeling there. So using that method I talked about in the second paper. Then you can also use the RPN filtering, right? So we're building filters. So we combine the two methods we discussed, create a set of filters essentially. And with those set of filters, we can then have that in place along with clip filtering. And then once we've kind of constructed our filters and ran those filters across the image data set, we've got a clip processing. So we've kind of eliminated images that clip says aren't good. Now we can do the weak supervision and kind of the ensembling approach there. So we've got all these filters we've created, apply them to the data set, form weak supervision, use the icing model, and then eliminate the images that the icing model says should not be included in the data set. And then from there, you've got yourself a data set now that has pre-labels to it. So you've taken a massive pool of data, refined it down. We can now take this massive pool of data and send it for either verification by humans or to get further labeled. And that's it. That's my talk. I know I covered a lot. Try to get through as quickly as possible, being respectful of other folks' time. Again, hands-on data-centric visual AI. Check it out. I talk about methods similar to this and a lot more. I'm going to do this talk as part of a larger workshop as well. If you want that workshop to come to your city, let me know. That's it for me, y'all.